evening, and thanks to the chairman and organizer to give me a chance to present our research here. So today my topic is Bandgap tunability and green boundary in 2D TMD materials. So I will present our two papers here. One is Nature.com published last year. The sample is a single layer MOS2, and the second one is published now this year, and the sample is different. And so, okay, at the beginning, I would like to say a little bit about the grain boundary. Grain boundaries in 2D materials is usually a nice bed which forms the regular interface between two single crystals for grain, and it's quite common in all the 2D crystals, both different measures, things like PVD, MDE, and also other measures, and also can observe on different materials. So I put some examples here. So one is graphene. You can see the green boundary here, and MOS2 grows by CBD, and this one is MOSE2 grown by MDE measure. So all this, you can see that the atomic structure is quite different from the green domain, and also at the green boundary, the material properties change a lot. You can see this from the peer mapping, the green boundary appear as a dark light, and while in the STM image, the green boundary here is shown as a bright green boundary, means that the electron density is quite high there, and it is still a challenge to determine the different structure and electronic properties at atomic scale, especially for 2D TMD material for its symmetric structure and also some other properties. So the first sample is single layer MOS2. This sample was obtained from Professor Lilian Zhong's group, and they had us to prepare this sample on graphite for STM study. So here you can see from this large scale STM image, you can see this typical triangle shape of the MOS2, and the data profile reveal the height is 7 angstrom for single layer. And this is the general image from the domain, and we can see the surface is quite clean and uniform. And this honeycomb structure is from MOS2, and this one, the more pattern also observable as highlighted by this flat paragraph, and which is attributed to the orientation and also lattice mismatch between the top layer MOS2 and underlayer graphite. Also, the dye profile here reveals the lattice constant of 3.2 angstrom. That is much larger than the lattice constant of graphite. Then we also do some the electronic bandgap can be determined by the EID spectrum. So this one is a EID spectrum recorded on MOS2 surface. So this electronic bandgap is turning to be 2.4 electron volts, and this bandgap is quite larger than the optical bandgap measured by peer spectrum. So here is the peer spectrum scorpion, and we can see the optical bandgap is usually around 1.8 and 1.9 electron voltage, and the difference between the electronic bandgap and the optical bandgap is the exciting binding energy. So here we find an exchanging that exciting binding energy here is around 0.48 electron voltage, and this value also quite close to MOSE2, molecular MOSE2 on graphite reported by other group. And the reason for such kind of large exciting binding energies to be abandoned, like reduce the electric field screen and enhance covalent interaction, and also large effectiveness of the charge carrier at the low dimension TMD materials. So we also can see some multi-layer region in this sample. So here we see the single layer, bilayer, and trilayer, and light profile, we get the height for each state is 7 angstrom, and we measured STS on the different regions, single layer, bilayer, and trilayer. We see a thickness dependent bandgap trend here. So for the monolith MOS2, the bandgap is 2.4 electron volt, and then it reduced to 2.1 electron voltage by layer, and then 1.75 electron volt in trilayer state. The bandgap decrease with thickness increase is caused by confinement effect, and it's a common phenomenon for this two-dimensional TMD semiconductors. And also from this image, you already can see some green boundaries appear as brighter contrast. So now we propose some detailed study on these green boundaries. So this one is a typical green boundary at a single layer MOS2, and then we bring into this small area. And from this attendant resolution image, we can see that the right side and left side have different more patterns. Instead, the orientation are different, and the misorientation between them is only to 18 degrees. You can see here 18 degrees, and we do some we record the bias center SGM image at the same region, and find that the bright protrusion only appear at high scanning bias, and then it disappear at lower T bias. Like if I go to 1D and minus 0.5 volt, then the bright protrusion is disappeared. To better understand the electron topologic change, we do a series STS measurement across the green boundary. We do STS at these market positions. Then we find that the bandgap changes dramatically with the distance from the green boundary. So see the black curve and the green curve far away from the green boundary. The bandgap is 2.5 electron volts, which is corresponding to the normal MOS2. But at the center of the green boundary, the bandgap decreased to 1.55 electron volts. So a decrease of around 0.85 electron volts is attempted here. And here is another typical green boundary. This one is difficult to find out because you cannot see the bright protrusion at the green boundary, but it's easier. It can be identified by the different mode pattern. So, for example, here in this green strip, the orientation difference between the mode pattern and the MOS2 cluster is 20 degrees, and at the right side it is only 8 degrees. So, and then a very small misorientation angle here, just about 3 degrees. And we also do a series STS spectral across the green boundary, and here only a very small decrease is observed. The change is only minus 0.17 volts. So we plot the bandgap change with respect to the distance from green boundary here. So we can see that when the distance is larger than 4 nanometers, the bandgap is 2.4, and then as the T approach to the green boundary decrease a lot. And also the decrease change is depend on the orientation angle. And the bandgap modulation here is a result of string effect combined with charge to 4. We do some DFT calculation, and from this panel you can see the bandgap decrease with the tensor and also compressive string. The minus is tensor and the plus the negative is produce compression, and the positive is tensor string. And from both sides bandgap decrease. And here the conduction band shift downward and balance that shift upward. But from our experiment data, we see that both the conduction band and balance band shift upward. So it could be some charge transfer from the defect or from substrate could take part in this bandgap change. And also the strain effect also can explain why the angle dependence of the bandgap decrease. So it's understandable that in larger misorientation angle, the lattice distortion of is larger than the smaller angle case. So the large distortion we have to use a larger step. The second example is monolayer tungsten biselenide. And here the sample comparison is a little bit different from the first one. Here the first one, the sample was blocked directly on graphite, and this sample is blocked on sapphire first and then transferred to graphite substrate for SPM measurement. So we also need to verify the cleanness and uniformity of this sample first. And from this training resolution image and also the STS, we see the quality is still quite high. And yes, we also can see more pattern and the edges of the WSE2 here. And the bandgap here is around 2 electron volts, which value is quite close to other groups. So also we can observe the green mountain over the surface. So you can see this image for different green mountains, and only those angle green mountain are found here. So and this boundary is quite different from the previous one. You can see this green mountain is shown as a dotted line, and the bright protrusion is decreased. So and also from this enlarged image, you can see the bright protrusion shows butterfly feature, and for the 4 points and for the different degree green mountain, these features are quite similar. And also to compare analysis, you can see that the interface between the location code depend on the misorientation angle. Usually is increased with the decreased misorientation angle. So we do some detailed analysis in our paper. I will not go to much detail here. So this angle dependence can be understood as Doppler model for low angle green mountain. So you can just refer to our paper for more details. And I'd like to just concentrate on the change of the electronic property here. So here we also again we do some bias dependent scale image here. We vary the scanning T bias from -1 to -0.8 to -0.5 and then 0.6. So you can see that this butterfly feature only appears as predicted T bias, but it appears as appear in the negative T bias disappear as predicted bias. So it means that the electronic structure is changed and contributed to the butterfly structure, butterfly pattern. And then we do STS at different positions around this preliminary defect. We also observed a big change of the BIDV curve. So you can see the multiple gas state are arrived on the dislocation curve, like 4 and 5, recorded on top of this butterfly structure. And also, this band edge shift further away from the Fermi level. And similar changes are observed on the different green mountain. So the observe the multiple gas state here and achieve of the balance band, and but the position of the first gas state is a little bit different. This gas state is located at 0.52 electron volt, and this one is closer to minus 0.34. So as the STM image is similar and also the change of the CIDV curve also similar, we assume that the tiny structure of this green mountain effect are to be the same. So based on our atomic result STM image, we propose such kind of four-member critical structure for this dislocation core and perform some DFT calculation. Preliminary calculation was performed on the plate model that we put this dislocation core at the center, and this four edge, the four edge of the plate is ready for relax. We also try different model, like including another four-member model with sterilized backing sheet and 5A5 drain 6A ring and also a 5-7 ring. So the calculated P dose is stored here, and we find that only the motor E is agreed with our experimental data. That only that some gas state appear at the balance at the close to conduction band, but for the other case, gas state are found on the balance band side. And also we simulated the STM image for this model, and this it shows a distinctive butterfly pattern, also consistent with our experimental data. And further calculation was performed based on Riemann model that we place the dislocation core periodicity along this Riemann Riemann, and with different rotation speed is variable. Then we also calculate the STM image at different lights, also consistent way with our light dependent image. Then this one, this result here is based on our Riemann model, and we can see the doodle. We call it as doodle that stands for logis and occupied defect orbital, as is here quite localized using around the defect dislocation core, and we can see a very good agreement between the theoretic calculation and experimental data. And finally, we also evaluated some factors that can influence the energy level of the gas state. We consider the disorganization angle and also applied chain. And from this calculation is based on the Riemann model. So from this simulation, we see that only a small variation of the energy of the Rudolph energy is observed. This one is somehow is not agreed with our experimental data because a bigger variation is fine, and but still understandable as calculation is based on Riemann model, and the strength can be dashed to the free standing edge, but in our experiment the strength cannot be dashed. So indeed we see the strength can change the energy level of the noodle. So as shown here, we apply a strength for different case with for different speed. This is the intersection between the location core. So we can see this the energy level decrease with the strength. And for this three case, we consider here the slots are quite close. The slots are almost the same. Okay, so now go come to my conclusion. So we use STM and STS to investigate the atomic and electronic structure of this the MOS2 and WSE2 and their green boundary defect, and combined with this calculation, we can obtain a quite good comprehensive understanding of the nature of this green boundary defect. And as we can see, the electronic property can be changed domestically at the green boundary. We find some Bandgap decrease and also get state and so on. And also the formation of green boundary are quite depend on the those natural substrates and also other related preparation process like in MOS2 we observe this with oriented angle and also small one. But on the WSC2 sample we only observe a low angle green boundary. So okay, so that's all. Thank you for your attention.